We stick to the production and processing of biopolymers. Now let's have a focus on 3D printing capabilities with Yizumi's technology.
Hello and a very warm welcome also from my side to this biopolymer conference. The topic of my presentation today will be 3D printing of biopolymers, a holistic resource saving approach. And we will do that with Yizumi's Space A technology, which is for sure an industrial pallet 3D printing technology. My name is Nicolai Lammert and I'm in responsibility of the complete additive manufacturing technologies at Yizumi. First of all, I want to start with the complete topic of how can we sustainably produce parts and plastics processing. Here we have two different topics we have to take into account. The first of all is the use of biopolymers for sure. And the second one is that we have to enable a technology for resource saving production technology. In terms of the biopolymers, we have different possibilities like using really a bio-based renewable resources to produce that biopolymers, and to use polymers who are biodegradable and polymers who can be recycled for a second or third use. But for sure, my topic today is not biopolymers at all, but the machines to process that biopolymers. So the second approach here, the resource-saving production technology, is more or less what I am looking for. So what can we do here? At the end, our industrial pallet 3D printing technology we at Yizumi believe in is a single screw extruder, which is able to process standard thermoplastic pallets. And this single screw extruder is mounted on a robot technology. And our approach is then fulfilled with a drying, a pre-treatment technology, so that our pallets have ever the same conditions in advance. So let's have a look on the process we are talking about. So you see here our extruder on the left side right now, and how the deposit strand solidificate during a 3D movement of the robot. And thus we have the possibility to generate a 3D printed part. We can do that in a really automated way. So you see here also in our approach that we have the possibility to go in a line integration, like you see with that piece carrier system here. And that is here a manufacturing cell 2 years ago at the Formnext, so 2018. And we were more or less the first production technology this time, which was able to produce complete parts autonomously. So every 35 minutes, we produce such a part. So another topic is for sure not only the 3D printing of three-dimensional parts, but we can also functionalize different parts which are perhaps molded in a pre-process, like, for example, injection molding or die casting. We showed that last time's K-Show, 2019 in Düsseldorf, in two manufacturing cells. The first one here is a sealing structure or anti-slipstick structure on a Raspberry Pi cover. It was on the booth, on the project booth from the IKV from Aachen. And the second one was at least an approach on our own booth at the K-Show, where we create a sealing structure on that engine cover you see on the right side. The video is right now running. So here you see the complete performance of that manufacturing cell from the Institute of Plastics Processing. And afterwards, you see that part move in our printing cell, and we were able to applicate that structure on this Raspberry Pi cover. So you see, additive manufacturing, for our understanding, not only mean that we can print parts, it also means that we can functionalize parts in a different way. Last slide, we saw the possible line integration using a 3D printing approach. And now I want to focus here a little bit more the possibilities of really 3D printing. And here you see that the additive manufacturing technologies are able to produce really fine and precise parts, like the hybrid fixture system at the bottom side, then the grippers in the middle, and the bicycle frame, which is more or less produced in a high-speed approach. And you see that really good in the comparison of the layer height, but also the nozzle diameter, the weight, but for sure the production time. So it's definitely possible with the screw extruder approach to produce really precise parts in for sure a long time, but also to produce parts in a really high speed, where the requirements are not that strict than for that hybrid fixture or gripper technologies, for example. So let's have a look more or less on the cost calculation, because that's also the basis of any sustainability discussion. So here you see the part of the video before, and you see that we are able to produce that parts in these boundary conditions for roughly 2.5 euro per part. That's one of the most critical elements from my point of view, why additive manufacturing is not that often used in real industrial use. For sure, we use 3D printing in the industry, but to use 3D printing for serious production and plastics processing is right now not state of the art, and the main factor is the pricing. And for that, we can only have a look on competitive technologies like injection molding, but also like other 3D printing technologies. And here you see more or less that we have really to handle a magnitude shift in the cost of that parts. And that's really depending on different aspects. I want to point out in this slide here. So what we see here is on the left side the part costs in euro per kg part weight, and on the bottom side we see the annual throughput per machine cost ratio. So that is more or less a cost ratio we implemented here, so that we have a more usable value at the bottom side. And what we can see is that we have different technologies compared to their ratio of annual throughput and machine costs. And you can see that for sure the speed and the invest of such systems are really important for the economic use of that systems. But what really visible here is that the main aspect is the material cost. So that means if you have a cost-intensive material like that 120 euro per kg material, then for sure we will not be able to produce parts with 10 euro per kg part weight cost. And that means that we have to use, at the end of the day, to reduce the part costs in our additive manufacturing processes, materials which are really nearby standard materials we also use in competitive technologies like the injection molding. And that means we have really to use pallets. Otherwise, we will be not able to meet a serious production price, for example, like we can offer in injection molding processes. The next point is for sure the throughput. You can see that a higher throughput can more or less reason also a higher invest. So we have more or less the same economic ratio here. But at the end, you also must consider that there are different forms of the material. So if you have a filament, if you have powder, or if you have pellets, it's completely different in the handling of that materials. For sure, the handling of pellets is really easy and really safe, more or less. And if you have the handling of powders or filaments, you have to invest a little bit more to get the same result at the end of the day. If we right now have a look on a specific part, like that eye panel carrier on the right side, you see that we have really strict costs, required part costs here. So that part on the right side with 5,000 gram, more or less, has to be produced for under 80 euro. Otherwise, it will be not economic for the OEM at the end to change the production. And if we compare that requirement and part size and part weight with the possibilities we discussed earlier, then we will see that the only technology which is really able to meet that requirement in a theoretical way is a Pallet technology, or named here as our Space A technology. And that means we need a game-changing technology like that Pallet additive manufacturing. Otherwise, we will be not able to go further on. Another point here is for sure also the part design we can discuss afterwards, but not in this presentation. Due to the fact that also this part design we saw on the right side will be never produced economically in additive manufacturing, since we have a lot of movement situations in that part without printing, and that means we have a lot of production time without printing a part, and that means we waste more than, in this case, in this example, more than 95% of the complete production time and moving around without printing that part. And that means we lost a lot of efficiency. And that means we have to focus in the future also a little bit more on the part design. Anyway, the Pallet extrusion technology based on robots give us a lot of benefits. And here you see the benefits at a glance. You see the scalability for sure. So we can really scale our system based on the part size. We have a good material diversity due to the fact that we can use any pallets in that screw extruder, so there are no restrictions. Due to the high productivity of single screw extruders compared to filament extruders, we are really fast compared to standard way of additive manufacturing. And what's perhaps the most important point for the future is the high potential of automation. So it's really cool that you can integrate that robots with that screw extruders and for sure our complete control unit in a line. So that means different robots can work together on different parts, or you can really follow up the lean production approach, which is for sure a sustainable way to produce in the future. One last point to that specific topic here. Our systems are ever used in a modular approach, so that it's really easy and really economic to switch them, to switch productions. The efforts of time consuming is really, really low, and that means you can really adjust your production fast to new situations of the market. What's right now the key aspect to be sustainable or to save resources, more or less? What we saw for our technology as a big basis is the lightweight extruder technology. That means we have a really small and light extruder, less than 7.5 kg of load. And that means we can really use also small robotics, which for sure save energy, but also costs in the production of that machines. And we have a really low energy consumption within that extruder, really low, really high throughputs possible compared to that energy consumption and the extruder weight. And at least additive manufacturing at the end has also less startup scrap. But for sure, if you have a small extruder, you have also less startup scrap. That gains some advantages. For sure, we can create a modular platform strategy due to the fact that we have that small extruder. It's not that the situations that we have to use a big robot anyway. So we can really decide to find the right robot for a specific situation, specific requirements. That means we can really reduce all efforts in terms of machine production, in terms of steel included in our machines, in terms of that required part size, required production situation. That means also that we can go forward as a symbiosis of machine and automation approach that really leads us to the topic that we can produce that machines in a serious production approach, really cost efficient, but also with a really small environmental footprint. And for sure, like I mentioned before, we can use the best size system for each product size. Only to give you a small hint, what are the power demands are. Right now we can produce with under 0.8 kilowatt hours per kg part size. And for sure, also our systems are really, really light. So you have, on a resource level, really not that much resources integrated in that complete machine, compared to perhaps a big injection molding machine with several tons of steel needed to produce that system at all. Now I want to have a further look to resource-saving production techniques and why perhaps 3D printing is really a good counterpart of primary forming technologies. If you compare the situation on the left side for primary forming techniques, you have not only the part design, which is more or less similar in 3D printing, but then you have to go forward with the mold design, CAD, simulation, CAM. Perhaps you have to create a bigger automation cell around of that molding machine. After that, you have to produce a perhaps really cost-intensive mold, which for sure has a certain environmental footprint. And then after a few months, you can start the production. In terms of 3D printing, it's really easy. You have your part design, then you create the CAM data. It's done in perhaps 20 minutes or 30 minutes. And then you just start the production with the machines you have in your plant. So there's no need to go forward with different other fixtures, molds, or something like that. So you're really fast and you have really less efforts in doing so. That means you have different resource-saving aspects, less design resources needed, for example, the mold design, less production resources for sure needed because of the mold, for example, less production resources needed for sure for the machines. Just compared the size and the weight of different machines, of 3D printers and primary forming machines. You all know the size and the weight and everything else around that machine. Less infrastructure demand. So for sure, you can just connect the printers with your electricity at your home place. So there's really no big, there's not big a deal to run such printers, but it's a really big deal to run perhaps big primary forming manufacturing cells. And for sure, at the end, due to the fact that there is less resource needed in advance, you have less time efforts and you have a really fast time to market. Now I want to show a little bit what's possible if you combine 3D printing and use the use of biopolymers. Here we are using a biofiber silver natural look material from the company Biofiber. It works quite well, like you see here. And what we produced here, as an example, for sure, a lot of possibilities are right now on the market, or possible at the end. We produced here a pallet, a Venturi pallet loader. We make a design where we integrate a Venturi loader with a storage chamber at least, and you can just produce that parts in 85 minutes, more or less, something like that, in a really fast way. And you can for sure use also biopolymers for that. So right now, it's a task for you all. If you want to 3D print the different parts with the use of biopolymers, you can ever get in contact with us or with the company Biofiber. I think we will find a way for that. So you see, it's definitely possible to go in a good way together here. At the end, I want to run a short conclusion. So what we see is that the combination of biodegradable materials and 3D printing is more or less an efficient way to save resources and to reduce the pollution at the same time. For sure, save resources is a topic of machine manufacturers and within the production of that machines for sure. But we have also really good access to the way how we produce parts, and that's really the key aspect of how much energy we can save. And the biodegradable aspect here is for sure a really important point to reduce pollution, and that's a key aspect why I'm really happy that we can print that materials in a proper way. Pellet additive manufacturing technologies can for sure directly process original pellets without further pre-processes. That means we have no second heat, and for sure, due to that, also no energy consumption for a filament extrusion process or something like that. There's only one heat, and then you have your part. The Yizumi approach means also that we have a very simple hardware approach, but a smart software technology in order to save the resources and machine manufacturing, but to gain at the end the standard ergonomic usage at the same time. So for sure, we are searching for smart techniques to combine that resource saving aspect with the same level of ergonomics at the end of the day. The Yizumi plasticizing technology has very low energy consumption, so we really focused on the topic of creating a cost reducing, a really simple extruder, but with a really clever design, so that we have a reduced energy consumption also during the plasticizing of their materials, and for sure the whole systems are scalable by the part size demand, and that means we can reduce the complete efforts calculated on a specific part. Thank you very much from my side. I hope you have had a nice conference here at all, and I wish you all the best.
Yeah, Nicolai, thank you very much for this interesting presentation to see that you have used the award-winning biofiber silver material for the trials to generate the 3D print. I think the audience has several questions, and let's see what they are looking for.
Hello, a very warm welcome from Merseburg, Nicolai Lammert from Yizumi, Germany GmbH. Good afternoon.
Good afternoon.
Are you ready?
Also hello from my side from Aachen.
Okay, thank you very much. Are you ready to answer the questions from the audience?
For sure.
Okay.
Great. Hi, Nicolai.
Hi.
You've explained very much in detail about the technical small things and the very well thought technology setup of the Yizumi machinery. One of the question is from the audience is, can the printing chamber also be heated for several prototype production, and will this also bring a benefit to the part quality?
So that's at least one of the key questions I ever got. The point is, so we will not provide a printer with a heated chamber. So we have for sure heated building platforms, that's clear, but heated chambers are really perhaps not the best way to save resources or to save the energy consumption here. So our goal is ever to process the material in an open way, so in a free environment around the machine, that give us a possibility to be that at least sustainable. For sure, it's not that easy to handle the process, but not only because it's easy. It's not easy. We shouldn't. So we should do that. From our experience, I think we ever find a way to process a certain part right now with different materials, and I speak like polyethylene, polypropylene, up to really high temperature thermoplastic materials. Right now we process all the materials only perhaps with a heated building platform, but not with a heated building chamber.
Mm-hmm. Yeah, thank you. But I can imagine if you want to have a thermal insulation to heat the chamber, and if it's not necessary or you're not using that, you have more freedom in space. So can you also get us a size of maximum part size what you have produced already?
So a maximum part size we produced perhaps 1.5 to 2 meters, something like that. So that is very free. You are very free in the space, because you can also put the Q car on the trail, and then you can process bigger parts. Like I mentioned, we have other techniques and other process techniques to get perhaps in the terms of semi-crystalline materials, a good layer adhesion, because that's the most important point. If you're talking about a heated building chamber, for sure you have to deal with the warpage, but the layer adhesion is a problematic situation in terms of the mechanics of that part. And here we have other techniques possible. So you can play a lot with the layer height, you can play a lot with the nozzle temperature, with the throughput, with the layer build time. So right now we find ever good solutions to go forward. The other point is, if we really go forward with an heated building chamber, then perhaps we build a machine which is 3 times or 4 times increase the price of the machine, and you are not so fast because you have not that heat transmission out of the part. That is mostly the problem here, and both aspects together leads to a really bad economic situation, and mostly a bad economic situation means also a bad sustainable environmental situation.
Maybe it's a very similar answer to the next question, but I like to pose it. Dinara from Russia is asking, could you tell please if a single screw extruder is more performable for processing of the biopolymers than a twin screw extruder for your 3D printing?
So at the end, for sure, we have often the question also internal that if we use other screw extruder technologies, the point why we ever decide to go the way we go right now is that we have a lightweight extruder, and that's really important for our approach to address or to use also small size robotics, because for the most plastic parts, to be honest, a small size robot is completely enough and okay. So to use the complete benefit in terms of the economic but also environmental situation, we need to reduce the extruder weight. And if we're using twin screw extruders, for sure we can think about better options in terms of throughput and something like that. But then we will have to use a really big robot that increase the price, but also for sure the power demand and everything around the resources to produce that machine. And like I mentioned, we process in a good way right now all that materials, and we have not so often the problem that the throughput is too low. So the question is ever there, can you make more throughput and more throughput and more throughput? But for the for most processes, we never use the maximum throughput we can use right now with our screw extruder, because the process is on a completely different level. So right now, not the screw extruder is a bottleneck. So from that point of view, it's perhaps not that that sensible to increase the extruder only because we need it bigger and with more throughput.
But here comes another question also regarding the performance of preparing the melt for the processing. Is there a limitation in the maximum fiber content of the pellets in regards of glass fiber or wood fiber, whatever? Have you seen any boundaries in that regard?
So right now we didn't find the boundary. So we go up to 60% carbon fiber or also glass fiber. So that's also possible. And in terms of materials with some metals inside, we go even up to 80%. So that's really surprising how good that works, more or less. So that was even not an unexpected point also from our side. But in terms of the filling percentage, we didn't find a boundary right now.
Great.
So also feedstocks, something like that, and that feedstocks are the most critical things, I think, from my point of view right now. It's also possible.
Great. So another question is more about coming from Christopher. Do you see your machines more manufacturing one product on the machine, or can you manufacture several different parts per day? how long does it take to run a new part in comparison to a normal FDM machine technology, e.g. from Stratasys, for example? Can you get some insights about that?
So two ways are possible. For sure, we call it right now the high-speed process. That is what is the most economic way to produce. So we are really fast. There we can calculate with roughly 1 day to get the setup for a new part. But that is more or less also the process for not for a part 1 production, but perhaps a variant production or with a series production. We also, if you go on LinkedIn on our Yizumi Germany channel, you can see we just did it for Volkswagen together with Faurecia. There we produced a part for the automotive industry, 820 gram, 24/7 production over 4.5 weeks, and with a cycle time of roughly 75 minutes. So we are really in a production situation then. And the other point is FLM process. For sure, we can make a really thin nozzle on the process. We saw that on one slide, and can then run a really low layer height. And that's really, from a process point of view, really simple compared to that high-speed process, because you have less problems with the heat transmission, with the complete heat management. So it's really slow, more or less compared to FLM processes. For like Stratasys, I only name it because it wasn't the question. But FLM processes also are, compared to the high-speed process, really slow. And there it's way easier. From our experience, you can just go forward with the settings you put in our slicer one time before, and then you can just get the final part in the first shot. So that's what we know from that FLM-like process. But like I mentioned, it's really long duration, perhaps something for fixtures and jigs or something like that, but not for the mass production then. So we saw that in the part we can produce 820 gram in 75 minutes, but we can also process 60 gram in 3 hours. So both is possible. And the FLM process is easier, way easier, really.
Yeah. So one question here from Carsten. Do you, as Yizumi, offer in Europe machines for testing? Can you get us some insight how you deal with approaches from customers who like to test?
So right now we have different possibilities. Here in Alsdorf, nearby Aachen, we have machines where we can run feasibility studies. Then we have different sales possibilities. We sell machines for sure. That is our target for the future, for the main target for the future. And right now we have also rental possibilities, but also our Yizumi Space Academy. That means we have 2 academy cells completely closed, so that you have your NDA restrictions, so you can go with NDA restrictions inside, and there you can just use working days on your demand. So that's really free of your charge. So we have different possibilities because we know that we have a complete new technology. Everything is really critical because nobody knows the technology, nobody knows the machine. Perhaps you have not that good contact to the Yizumi until now. And then you have to design perhaps your part in a complete different way. You have to use a material you never know before. And everything around that is for sure a critical situation. And due to that, we are really supported for potential customers or for partners, for material suppliers, or also for users.
Great. Sounds really good. So I assume you are the right person in charge to contact if it comes to those questions. So
yeah,
great to have you in that call today, and that you have answered all these questions from the audience. Thank you very much.
Thank you very much.
Thank you too. Thank you.
Have a nice
for that
day.
opportunity.
Thank you for joining.